Can you hear me? Yes. All right, yeah. I want to sort of bring everybody up to date on what we're doing with visualization. So we heard people talking about sort of the massive volumes of data that all these wonderful high-performance computing solutions are delivering today. And to be perfectly honest, you can compute all this stuff, you can store it, but at the end of the day, scientists really need to analyze the data, understand it in order to move forward. So we feel that interactive visualization is really a requirement now to analyze the flood of data that's coming from these systems. So there's two challenges there. One is, how do you provide visualization capability that's going to deal with data sets this big? And then the second challenge is, how do you make this available to all the scientists and engineers who are going to be using it? So we're really trying to address both of those issues. The first one we call Scalable Viz, where we're putting hardware and software together to enable you to scale systems up to deal with data of that size. And then the second is some shared visualization software that we provide so that people from any client, from a Sunray client to a Mac laptop to your desktop machine, can then have access to applications running on this central visualization resource with high performance. So just sort of the problem statement is, the data's too big to really deal with on a workstation, on your desktop anymore. The first problem is getting it over the network, getting it down there. Second problem is then you have to have high performance graphics, lots of memory, and it just gets to be a noisy, hot, large problem to deal with. So we think that it makes more sense is to change the model and make it easy for people, for users on the network anywhere, to have access to a highly scalable graphics resource. So we started this work about 4 years ago, actually, at University of Texas Tech, and we built a visualization system sort of based on the biggest system that Sun sold at the time, which was an E25K, and put high-performance graphics cards on that system. And then started trying to solve the real problem, which was, how do you make this available to lots of users so that they can share the resource, so it appears to them as something that they can have exclusive access to, even though they're not, and how to make it transparent so that their normal applications that they were used to using, they could have access to. And this is sort of something that's been going on and is still in use. There have been people outside the TeraGrid research community, extending to people like University of Texas Southwestern Medical Center, using it to look at 3D protein structures from cell biology. So it's been an interesting exercise. It was a good research collaboration, and like not all research collaborations, it actually ended up in a product. So Sun is now selling what we call our Sun Visualization System 1.0, which consists of our Sun shared visualization software, which provides this transparent access to 3D applications, which then can run on a central resource. And then also, that's kind of the software access part. The other part of this is building this large-scale visualization resource, and that we call our Sun Scalable Visualization Solutions. And this is a combination of hardware based on Sun servers and NVIDIA graphics, and then a software stack that lets us scale beyond one device to many devices, and those many devices may be in many systems. So first, the Sun shared visualization software. So that's actually a software stack as well. It has a number of different parts. It has the basic engine of it is something called VirtualGL, which is software which basically sits at the OpenGL layer and transparently intercepts the OpenGL calls to run on the hardware with high acceleration, and then read back, compress, and send to the client. The Sun Grid Engine part is what makes this more than just a one-to-one remote sharing. It allows you to have multiple users access the same resources and manages and makes it easy for the user to work at his desktop and not have to worry about which system with which graphics and do all the work to get it back to their screen. So I'll tell you a little bit more about this. But basically, like I said, it's application transparent, and the main goal of it was to make this be as high performance as possible so that the experience of the user was really much the same as if they were really actually sitting in front of this scalable visualization resource. It is a community-driven project. It's based on the VirtualGL open source project, which is sponsored by Sun. So some of the advantages of doing things this way is, one, instead of sending your 100 terabyte seismic, 100 gigabytes, sorry, or more seismic visualization data set down to the workstation, you can basically tightly couple the visualization system with the compute and the data system, and then only send the rendered pixels. We're taking advantage that 3D rendering is actually a data compression, data reduction process anyway. So all you're doing is sending those pixels to the screen. It also enables collaboration because now multiple people at different locations can be looking at the same application interface and interact together to see the data. And it does have some security benefits because now instead of sending that raw data down to somebody's laptop that could be walked off with, it can be kept centrally secure with only the pictures and images being sent to the ultimate client. So how does it work? So basically the application will run on a system that runs OpenGL and X applications. In our case right now we support both Solaris and Linux, so that's Solaris Spark and Solaris x64 on the server side. On the client side, there's a little piece of software which basically takes the pixels and uncompresses them and displays them on the screen. And this client can be a Mac laptop, it can be a Spark workstation, it can be a Windows laptop. Really a wide variety of clients are supported. It has full OpenGL support, so we also support stereo and overlays, and it does support SSH and SSL. So one of the things that what this does for us is basically say I can have my access to my very high performance visualization resource wherever I might be. It actually works as well with our Sunray very thin client. In this case, we take advantage of the fact that we know what the Sunray protocol is and we know what Sunray is capable of. So we send the images directly to the Sunray client using our Sunray plugin. If you didn't use the Sunray plugin, VirtualGL would work as normal, but you would be sending all of the OpenGL rendered pixels back to the Sunray server and then on to the Sunray client. So on a wide area network, we support something called Turbo VNC. And in this case, wide area network latencies are usually long, which makes remote X protocol problematic. So in this case, we use a version of the widely known VNC, which has the same kind of very optimized compression that VirtualGL uses and sends it directly to the client. So this also gives us the ability to do collaboration because now you can have more than one client can connect to the same Turbo VNC session. And again, this is another open source project that's sponsored by Sun. And so then the last piece is the Sun Grid Engine with enhancements for shared visualization. In this case, it looks really complicated. So the message is really that all of the stuff in that gray box is sort of the magic that makes the user not have to be aware of how do I find which resource is available and where is it and how do I send the pixels back to me. That happens transparently to the user. So that was our Shared Viz 1.0. We're right now coming up with some improvements to Shared Viz. And our main goal really for this release has been to improve the usability, make it even easier for people to install this on their systems and use it. And the other part that we've added to this is to improve the performance. So performance on Solaris has actually been the major focus. So now we have, Spark has improved about 25 to 30%, and our Solaris x64 performance is now equal to the Linux performance. As well, because similarly, the Turbo VNC performance has been, thank you, improved. So this is actually beta-ing starting next week, and we're going to be releasing it at the first of the year. So the other part now is the Scalable Visualization solutions. And this is where you want to be able to build a graphics server, if you will, that can scale with these large-size data sets. So this might mean using a bigger system, a system with more CPUs and more memory and more graphics devices, or it also might mean InfiniBand clusters of these systems with software that lets you run applications across the multiple systems. So the problems that have been trying to solve is, okay, one, we want to use a big system, but big systems don't often allow you to plug big, power-consuming, hot graphics cards into them. So the first solution was the same one that we used back with the Maverick system, which is get the graphics card out of the system. Fortunately, NVIDIA had the same idea, and we're now using the NVIDIA Quadroplex, which is two of their top-end graphics cards in a box, which then runs PCI Express over a cable to a very small, low-power card that fits into the PCI Express slot on the server. The second problem would be when you want to look at images with very high resolution and spread them across multiple screens. So in this case, one of the solutions is to use multiple systems in a graphics cluster to do that. So we're providing software to help enable that. And then the third problem is actually probably the hardest one of all, which is to try to get really good and interactive performance on rendering very large data sets. And so there's a couple of different approaches to this from software, pretty much breaking them up, the problem up, and distributing the rendering among multiple nodes. So we have actually a supercomputing demo of this last thing, which I invite everybody to come see. So we're going to be showing a 16 GPU cluster based on our Ultra 24 with our new Intel workstation with NVIDIA Quadroplex, and we will be actually splitting this InfiniBand cluster into two pieces. So one piece is going to be in the Intel booth and one piece is going to be in the Sun booth, but they're all going to be working on the same problem, rendering a very large scale seismic data set and a very large CAD model. So anyway, so the thing is, this is the vision. The vision is basically that you can go from a workstation with high performance graphics to larger scale systems with Quadroplex providing the graphics to InfiniBand clusters of these systems. The Scalable Viz 1.1 software provided a complete software stack for Red Hat Linux. It was really based using Chromium, DMX, MVA Pitch 2, and the Open Fabrics for InfiniBand support. And it also included a couple of applications and a ParaView and Open Scene Graph. This is all open source software. Basically what we did is provide a complete tested, integrated software stack and then made it easy to install and use. And then the last part of this was to integrate it to allow shared viz jobs to actually run on such a graphics cluster. So the 1.1 software, which is also coming out soon, is really add support for Solaris x64 and also for Red Hat 5. So we updated the software components inside this to have the sort of latest capabilities. And then we added a couple of new features. So part of what the Scalable Viz software does is help in the configuration, determining the configuration files which allow you to create a graphics cluster. And what we've done with 1.1 is allow you to define pieces of these graphics clusters that can be used individually. And what that means is if somebody has a 16-node graphics cluster, it can be used all at once, or somebody could use it as 2 nodes of it at a time, or another 4, or separately dividing it up. This makes it a much more useful resource to be used in conjunction with our shared viz software. And like I said, this is going to be released in February 2008. So along with the new software, we also have some new hardware that's supported with this. Like I said, our Ultra 24 workstation is going to be a low-cost building block for graphics clusters. We'll also be supporting our new Intel-based servers, the 4150 and the 4450. And then we have some new next-generation Opteron servers that will also be supported. There's also a couple of new NVIDIA products along with this. One that's very interesting for the shared visualization market is the Quadro S4, which is 4 GPUs in a 1U box, which gives us a nice, dense form factor for building a visualization server. Also, along with this is Quadro Model 4 has been out for a little while, but NVIDIA has just recently substantially reduced the price for this, so that really makes it a really more attractive a part of a visualization solution. You heard NVIDIA talk about their GPU computing solutions. Like I said, we're working with them in providing compute solutions together with their GPU computing solution in combination. We've tested out the D870 with the Ultra 24 and the Ultra 40, and also their server S870 with our X2200. There's going to be a CUDA developer special based on the Ultra 24 and the C870 card, which plugs into that system, which should be really interesting. And one of our just very recent, in the process of being delivered, GPU computing solutions is a UNC Chapel Hill cluster. In this case, they have a compute cluster that's integrated in with GPU computing. So about 2/3 of the cores are just standard systems. The other third has to do, are directly connected to NVIDIA Quadroplex boxes for doing GPU computing. And I want to invite you to come and see all of this stuff at our booth in supercomputing. Like I said before, we'll be showing scaling visualization performance. We'll also be demonstrating our Solaris version of Scalable Visualization in conjunction with GPU computing and shared visualization. And thank you very much.
Thank you very much.